Hello everyone and welcome back to Exam Ignite YouTube channel. This is Embedded System Design subject of 6th semester of code BEC601 Module 4 Part 1 video where we'll be covering the ARM embedded systems. This is a completely different from the first half that we have studied in the Module 1, Module 2 and Module 3. This has a separate textbook, and from there you are having chapter 1, 2 and 3 for the syllabus of this embedded system design. So firstly, we are starting with the ARM embedded system introduction, then RISC design philosophy, ARM design philosophy, then embedded system hardware, that is AMBA bus protocol, ARM bus technology, memory, peripherals, then embedded system software, that is initialization, boot code, then operating system applications, then the ARM processor fundamentals, ARM core data flow model, registers, current program status register, then pipeline, exceptions, interrupts and vector table, then extension, that is core extension. So these are all the topics that are present in this module, and here the important topics that we need to go through here is, so that is been listed here. So they have asked in the model question paper in the June-July 25 question paper or in the December 25 Jan 26 papers. So I have referred 3 to 4 papers and marked the important topics here. You can mark it down to study further. Starting with the module 4, first is ARM embedded systems. Here the RISC design philosophy. So ARM core uses a RISC architecture, we know, that is reduced instruction set computer, is a design philosophy aimed at providing a simple but powerful instructions that execute within a single cycle at high clock speed. So in the RISC philosophy, more intelligence is placed in the software rather than hardware. Hence, RISC places greater demand on the compiler. So whereas what is CISC? It is complex instruction set computer. It relies more on the hardware functionality and uses more complicated instructions. So we can see here, this is an RISC versus CISC. Here CISC emphasizes hardware complexity and RISC emphasizes the compiler complexity. Next, coming to the major design rules of the CISC is first instruction. So RISC processors have a reduced number of instruction classes. It is simple and fixed in length and helps in pipeline execution, but reversed in the CISC. Then pipeline. So here instruction processing is divided into smaller stages that they execute in the parallel using the pipelines. Hence is a faster and high throughput can be observed. Then registers. Here the RISC machines have large general purpose register set. So registers here they store the data or address on the fast local memory. Then load storage architecture. Here the processor works only on the data stored in the registers. Separate load and store instructions are used to move the data between the register bank and the external memory. So this improves the performance because data in registers can be reduced without repeated memory access. So then the ARM design philosophy. Here ARM processor was designed specifically for the embedded applications. Why? They are having some of the physical features influence the ARM processor design. What are those? First is low power consumption. They operate on the battery power. Hence, they are designed to consume the less power and extend the battery life. So applications they include, one is mobile phones and the personal digital assistants. Then high code density, that is nothing but they have limited memory. Like ARM provides high code density, so it is making it suitable for the mobile phones or the mass storage devices. Next, the low cost. So it is cost sensitive and often has slow memory and low cost memory devices. Then comes small chip size. So single chip solutions reduce the PCB area. So this means more area for peripherals, reduced manufacturing cost. Then hardware debug support. So ARM processors include the hardware debugging technology because better visibility of processor execution and easier software debugging are faster issues resolution. So this reduces the time to market and development cost. Next is ARM core strength. So ARM is designed for the embedded system where there is a low power consumption and efficient performance are more important than the raw processor speed. So next is instruction set of the embedded system. So here in ARM instruction set differs from pure RISC, but supports better support embedded system. So first is variable cycle execution. ARM like the instructions may take variable execution cycles. So example like load, store, multiple instructions, transfer the multiple registers. So inline barrel shift here, ARM contains an inline barrel shift. So it pre-processes the input registers before the instruction execution. So next is the thumb 16-bit instruction set. Here it is introduced a thumb instruction set. It allows execution of 16-bit instructions and 32-bit instructions. Next is conditional execution. Here instruction execute only when specific conditions are satisfied. And the fifth one is enhanced instruction, like ARM added DSP type instructions for 16x6 multiplication or saturation operations. Next topic is embedded system hardware. So embedded systems control different devices ranging from the small sensors in the production lines and real-time control systems. So these systems use a combination of software and the hardware components. So each component is selected for the efficiency and the future expansion. The first is the ARM bus technology. So embedded systems use different bus technologies. So unlike the PCs, ARM buses are usually on the chip buses. So bus is integrated into a processor chip and allows the peripherals to communicate with the ARM core. So ARM processor role is ARM processor acts as a bus master. A bus master initiates the data transfer. Peripherals respond as a bus slaves. So there are levels of bus architecture here. The first one is physical level and the protocol level. So it defines the electrical properties like 16-bit bus or 32-bit bus or 64-bit bus, the physical level. Protocol level, it defines the communication rules between the processor and peripheral devices. So ARM mainly specifies the bus protocol rather than the electrical implementation. Next is AMBA bus protocol. AMBA bus is nothing but advanced microcontroller bus architecture, which was introduced in 1996. It became a standard bus architecture for the ARM processors. So first AMBA buses were ASB, that is ARM system bus, APB, it is ARM peripheral bus. So later the ARM introduced the AHP, that is the advanced high performance bus. So what is the advantage of using this advanced microcontroller bus architecture is standardized peripheral interface, easy peripheral integration, then it reduces the redesigning effort, it improves the hardware reuse and faster product development. AHP features we'll learn here. One is AHP supports higher clock speeds, multiple bus masters and better throughput. What is AHP variants? We are having multi-layer AHP and AHP Lite. Multi-layer is nothing but it supports multiple masters simultaneously, that is parallel operation. AHP Lite means on a single bus master. It is used for simpler systems. So an example of an ARM-based embedded device is a microcontroller that is shown here. Here it contains an ARM processor with an input controller and AHP arbiter. Then that is connected to AHP APB bridge. Then we are having memory controller, AHP external bridge connected to external bus. Then we are having real-time clock and a serial UARTs and Ethernets, counters or timers like this. So next is memory. Memory is an embedded system requires memory to store and execute the code. While selecting the memory, factors like price, performance, power consumption, memory hierarchy, width, type must be considered. So first one is hierarchy. Here computer systems organize memory in a hierarchical manner. So it is like CAC memory, it is the fastest memory and nearest to the processor. Main memory, it is moderate speed and capacity. So secondary storage means is slowest but has the largest storage. So you can see a graph indicating the performance or the cost versus the memory size. Next comes the explanation of each of that memory. Cache memory is placed between processor and the main memory. It speeds up the data transfer and improves the performance. But two limitations here is does not help in the real-time response and execution becomes less predictable. Main memory means it ranges between 32 KB to 256 MB or more depending on the application. Secondary storage, it is like hard disk or CD-ROM we use for storing large amount of data. Width. Memory width is the number of bits returned during one memory access. Like typical width will be 8-bit or 16-bit or 32-bit or 64-bit. It affects the overall performance and cost of the system. So let us take an example. If a 32-bit ARM instruction is fetched from a 16-bit memory, the processor requires two fetchers to fetch all that instructions, right? So if the 16-bit instructions are used with a 16-bit memory, then only one fetch is required, which is giving a better performance. So this matters a lot. So next we are having types of memory we learned in the previous itself, that is ROM, read-only memory, permanent data, and it is programmed during manufacturing itself, cannot be reprogrammed, and it is used for boot code or fixed firmware. Flash ROM, it can be read or written, and slow writing speed, and is used for firmware storage, that is software storage and long-term storage. Next is RAM, that is dynamic RAM. It is commonly used as RAM and lowest cost per MB and dynamic in nature, refreshing periodically to retain the data. SRAM is static RAM. It is faster than the DRAM and does not require refreshing, faster access time and higher cost. And next is SDRAM, that is synchronous DRAM. Here runs at a high clock speed, synchronized with the processor clock and data fetched in the burst mode. Next is peripherals. Here external embedded systems interact with the external world through these devices, like functions like input, output, and communication are done. Memory map peripherals are also there, where ARM peripherals are generally memory mapped. Next is memory controllers. They connect the different memories to processor bus. Like their function is to configure the memory during the power up and enable the memory access. Example is for DRAM, controller sets timing and it refreshes the rate. So before access is allowed. So next is interrupt controllers. Interrupt controller manages the processor input. When a device needs attention, it raises an interrupt. So it can be the interrupt controller decides the interrupt priority and in which handler executes. So types of ARM we are having is standard interrupt controller and another one is vectored interrupt controller. In the first one, it sends the interrupt signal to the processor itself and can mask or ignore the interrupts. But this VIC, it is more powerful than the standard one because it prioritizes the interrupts, simplifies the interrupt handling, and associates handler address with interrupt. Embedded system software, it controls the hardware device. So 4 software components are there. First is the initialization code, operating system, device drivers, and applications. So the software abstraction layers executing on a hardware device. So on a hardware device, we are having initialization and the device drivers which connect the operating system with the applications. So initialization code means it will execute the first after the reset and configures the board. It prepares the system for operating system. Operating system, it controls the applications, manages the hardware resources. Many embedded systems use only simple task scheduler, event-driven operation instead of full OS. Device drivers, they provide an interface between the hardware and software. Application performs the actual required task. So firmware, that is a software stored in the ROM, is called as firmware. Initialization, that is boot code. Boot code takes the processor from the reset state to a condition where OS can execute. Like it functions like configures the memory controller, configures the processor cache, and the initializes devices. So 3 phases of initialization. First initial hardware configuration, then diagnostics, then finally booting. So this is how memory remapping. Remapping is nothing but ARM systems often remap memory during the startup. So start the execution from the ROM and later remap the RAM to low address space. So this allows the interrupt vector table to reside in the RAM and be reprogrammed. Then in the operating system, it takes the control and it manages the peripherals, memory, and processor time. ARM operating categories are RTOS and the Platform operating system. Real time means it is guaranteed time response time and suitable for the hard real time. Platform operating time, it is rich memory management and general purpose applications only. And application are the programs dedicated to handling a particular task in the embedded system. So functions are given here. It implements a processing task. OS controls the execution environment. Multiple applications may run simultaneously. ARM processor applications are used in many market segments such as networking, automotive systems, mobile devices, consumer electronics, and in mass storage devices, etc. Some of the examples are given. Next comes the next main topic, that is ARM processor fundamentals. So here this will be seeing in the part 2 video of this. So thank you for watching. Do like, share and subscribe to Exam Ignite.